We're designing YouTube, a video streaming platform serving 2 billion monthly users with 500 hours of video uploaded every minute. It needs upload and adaptive streaming, search and recommendations, user accounts, and engagement features. At this scale, we need sub-200 millisecond latency worldwide, 99.99% uptime, support for 4K and 8K video, and cost-efficient petabyte-scale storage. Let's break down how to build this. Let's start with the MVP architecture for our YouTube-like platform. We have a simple setup with a web server handling user requests for browsing and playback, and an application server managing video uploads. PostgreSQL stores all metadata like video titles, user accounts, and search indexes. Amazon S3 provides object storage for the raw video files themselves. This straightforward architecture supports our core requirements. Users can upload videos, watch them, create accounts, and search for content. It's designed to handle around 1,000 concurrent users, which is perfect for our initial proof of concept and testing phase. As we scale to 1 million users, we hit critical bottlenecks. Video processing blocks uploads, database reads slow down search queries, and streaming from our origin servers becomes expensive. Here's how we address these challenges. First, we add a CDN for global video delivery, ensuring users' worldwide experience under 200 milliseconds latency when starting playback. We introduce a load balancer distributing traffic across multiple web servers for horizontal scaling. Redis cache stores hot metadata like trending videos and popular search results, dramatically reducing database load. To handle 500 hours of video uploaded every minute, we implement asynchronous processing with an SQS message queue feeding transcoding workers that convert videos to multiple formats and resolutions including 4K. Finally, we add database read replicas to handle the massive volume of search queries without impacting write performance. This architecture now supports our 1 million user milestone with excellent performance. At 100 million users and beyond, we face new challenges that require fundamental architectural changes. Our single database cannot handle the write load from billions of users, storage costs for petabytes of video are unsustainable, and search performance degrades. Here's our enterprise-scale solution. We implement database sharding, partitioning data by user ID across multiple database clusters. This enables true horizontal scaling for writes and reads. For storage, we introduce a multi-tier system: hot storage on SSDs for recent popular videos, warm storage on HDDs for moderately accessed content, and cold storage on Glacier for archived videos. This tiered approach reduces storage costs by 90% while maintaining performance. We migrate search to Elasticsearch, providing sub-second query times even with billions of videos. A dedicated machine learning service powers personalized recommendations. Finally, we deploy across multiple geographic regions, ensuring 99.99% availability and low latency worldwide. This architecture now supports our full-scale requirements: 2 billion monthly active users, 500 hours of uploads per minute, global sub-200 millisecond latency, and cost-efficient petabyte-scale storage. Let's dive deep into our storage system, which accounts for 60 to 70% of infrastructure cost at YouTube scale. At the core, we're using S3 for object storage, but S3 isn't just one thing, it's a tiered system. We have S3 standard for frequently accessed videos, costing 2.3 cents per gigabyte with instant access. This handles our hot videos, about 20% of total data. Then we have S3 Glacier for archival storage, just 0.4 cents per gigabyte, but retrieval takes 3 to 5 hours. This stores our cold videos 80% of data. The key trade-off here is cost versus access speed. Standard gives instant access but costs 6 times more than Glacier. For a video platform, 80% of views happen in the first week. After that, Glacier makes sense, saving us 95% on storage costs. Now let's look at lifecycle policies, the automation that makes this tiering work. When a video is uploaded, it starts in S3 standard for instant access. After 30 days, if view counts drop, it automatically transitions to S3 intelligent tiering, which monitors access patterns and moves data between tiers. After 90 days, videos with minimal views move to Glacier. This automation is driven by the 80-20 rule. 80% of views happen in the first week. The view pattern follows an exponential decay curve. By automating these transitions based on metrics, we optimize cost without manual intervention. Videos that suddenly go viral can be promoted back to hot storage automatically. Another critical decision is our transcoding strategy. When a video is uploaded in 4K at 10 GB, we immediately transcode it into multiple resolutions: 720p at 1.5 GB, 1080p at 3 GB, and 4K at 8 GB. This means storing 22.5 GB per video instead of just the original 10. Why do this? The trade-off is storage cost versus transcoding latency. Pre-transcoding means instant playback at any resolution. Users don't wait. The alternative is on-demand transcoding, which saves storage but adds 30 to 60 seconds of latency on first view. For a platform with billions of views daily, pre-transcoding wins. We optimize by only keeping popular resolutions for old videos. 720p and 1080p cover 95% of views. Let's dive into our CDN strategy, which is critical for meeting the 200 millisecond global latency requirement. The fundamental choice is push versus pull. Push CDN means we proactively upload content to edge locations before users request it. This gives lower latency and predictable load, but wastes bandwidth if content isn't popular. It's ideal for live streams and new releases. Pull CDN means edge locations fetch from origin on demand. This saves bandwidth and only caches popular content, but the first request is slow and can spike origin load. For on-demand videos, pull makes sense. We chose a hybrid approach: pull CDN with Origin Shield. Origin Shield is CloudFront's middle caching tier that sits between edge locations and origin. It reduces origin load by 70% by consolidating requests. Edge location coverage is another critical trade-off. To meet our 200 millisecond latency requirement globally, we need over 200 edge locations worldwide. Each point of presence, or POP, costs about $50,000 per month in infrastructure and bandwidth. The trade-off is coverage versus cost. More edge locations mean lower latency for more users, but each POP adds significant cost. We optimize by using CloudFront's existing network of 400 plus edge locations, which amortizes cost across all AWS customers. For regions with high traffic like North America and Europe, we get dense coverage. For lower traffic regions, we accept slightly higher latency. The coverage circles show the geographic reach of each edge location. Users within the circle get sub 200 millisecond latency. Cache TTL strategy is a critical trade-off between cost and content freshness. Short TTL like 1 hour means fresh content but high origin load. The CDN fetches from origin frequently, increasing bandwidth cost. Long TTL like 7 days minimizes origin load and cost, but content can be very stale if a video is updated or removed. Medium TTL like 24 hours balances both. For YouTube, videos rarely change after upload, so we can use longer TTL. Our strategy is 24-hour TTL with cache invalidation API. When a video is updated or deleted, we explicitly invalidate the CDN cache using CloudFront's API. This gives us the cost savings of long TTL with the freshness of short TTL. Cache invalidation costs 50 cents per 1,000 paths, which is negligible compared to bandwidth savings. Finally, let's look at our multi-CDN strategy for redundancy and cost optimization. We use both CloudFront and Cloudflare in parallel. CloudFront has 400 plus POPs and handles 70% of our traffic at 8.5 cents per gigabyte. Cloudflare has 300 plus POPs and handles 30% at 4 cents per gigabyte, about half the cost. Why not use only Cloudflare? Redundancy. If one CDN goes down, we automatically failover to the other using DNS-based routing. This ensures 99.99% availability. We also optimize cost by routing traffic based on region. In regions where Cloudflare has better coverage, we route there. In regions where CloudFront is cheaper due to AWS data transfer discounts, we route there. The multi-CDN approach adds complexity in routing logic and monitoring, but saves millions annually and provides redundancy. Let's explore how to build a YouTube-scale video streaming platform on AWS. Here's our complete architecture designed for billions of views per day. Starting at the entry point, we use Route 53 with geo-routing to direct users to the nearest region, paired with CloudFront's 200+ edge locations for ultra-low latency video delivery. The application load balancer distributes traffic across our web servers running on EC2 auto-scaling groups, ensuring we can handle massive traffic spikes during viral moments. Moving to our compute layer, we leverage ECS Fargate for containerized microservices, giving us the flexibility to scale individual components independently. Our video transcoding pipeline uses MediaConvert combined with Lambda and ECS Fargate workers to process uploads in parallel, converting videos to multiple resolutions and formats. For real-time recommendations, we deploy SageMaker ML models with Lambda for fast inference, while SQSQs handle asynchronous tasks like notifications and analytics. Now let's examine our data layer. We use Aurora PostgreSQL with custom sharding logic and read replicas to handle millions of concurrent users. Elasticache Redis in multi-AZ configuration provides sub-millisecond response times for frequently accessed metadata. For video storage, S3 intelligent tiering automatically moves content between storage classes, while older videos archive to S3 Glacier, cutting storage costs by up to 90%. OpenSearch Service powers our search functionality, enabling users to find content instantly across billions of videos. Taking a step back, this architecture delivers the scalability, performance, and cost efficiency needed for a global streaming platform. Multi-region deployment ensures 99.99% availability, while intelligent caching and CDN distribution minimize bandwidth costs. Tools like Cloud.ai can help you design and optimize architectures like this with built-in best practices, automated cost analysis, and compliance checks. At YouTube scale, expect monthly costs around $500,000 to $2 million depending on traffic, with the majority going to bandwidth and storage. However, the pay-as-you-go model means you only pay for what you use, making it perfect for platforms with variable demand. We evolved from simple MVP with S3 and EC2 to global scale with CDN and multi-tier storage. Key decisions: caching for performance, CloudFront for global reach, and S3 lifecycle policies for cost optimization. Start with the MVP, add CloudFront when you hit 100K users, and implement storage tiering to reduce costs as you scale.